Hello, in this talk I will show you one computer experiment, determination of the melting point of a model of rock salt. The chosen model is based on the Lennard-Jones interaction for both ions and charges. The principle of the experiment will be to prepare such an elongated periodic box which contains two slabs. In one slab there is a crystal, and in the second slab there is a melt liquid, and these may be at correct conditions in equilibrium. If they are not, so either the crystal grows or the crystal melts. We will use the standard Verle or leapfrog type integrator, the Anderson thermostat. I review that this is a thermostat where once a while I visit a particle and push it according to the Maxwell-Boltzmann distribution of velocities. We have charges, so it's necessary to use the eval-summation, and the barostar will be the simple Berenson type, and from the technical point of view the code will use the linked cell list method, and I have on my notebook 4 processors, so I will use all these 4 processes in parallel. The basic steps of the procedure with certain detours to show you the redistribution function and so on will be: first, to take such a small crystal, to replicate it, so we'll get a box. It essentially will be of this size with only a crystal inside. Then we need to determine the equilibrium box size so that we know what the size in this direction and we do not have any stress in the crystal. I will also show you the radial distribution function and other properties. I will do the same for the melt. But to determine the melting point, I will repeat this crystal in the z direction. In this case, this is the z direction, 3 times, so I'll get this elongated box, and I will melt half of the box by a special thermostat that will apply only to half of the box. And then a simulation will show me whether at the given temperature the crystal melts or grows. I have prepared 12 scripts to run all these simulations. Under normal circumstances, if hardware and software permits, students do all these steps by themselves on a remote computer or a remote cluster. I will do it by myself here. That is, the first step is to prepare a very small crystal which contains 8 atoms for cations and for anions. The first task is to calculate the size of such a crystal, and this is student's task, but now I do not have students here really. They are only remotely connected, so I will do it by myself. So the first step will be to define the density. I am using a calculator which understands units, so these are given in brackets. So the first one, and as regards molar mass, there is a function here. So the molar volume is given by the molar mass, and I need the molar mass of the cube I have divided by this density, and the volume is this volume mass, this molar volume divided by the Avogadro number. It's also included in this system, so we can review it easily, and we have the result. And to get the size, I calculate the cube root of the volume, and it is 5.7 angstrom. If you wish, I can convert it. So the result is 5.7, which should be entered here, and the script filled a box by these molecules. So this is our starting point. The next step will be to replicate this 3 times in each direction. There is a technical step needed here which creates a force field, but it's not necessary to describe any detail for you. And now the small crystal has been replicated 3 times in each direction, and 10 steps of a simulation will run. Well, it's very fast, of course, so I will show you the trajectory. So from the beginning the size changed a bit, it wasn't exact, and it started to move a bit. All molecules started to move by thermal motion. They should. Okay, so the next step is the initialization of a simulation of this crystal. So I will restart everything because it's been done the last year, and let's simulate a crystal. I will choose density which is in between of this recommended range. In normal circumstances, every student uses a different temperature, and if we compare the results at different temperatures, we'll get the estimate of the melting point in the end of the course. Okay, here you can watch a file which is used for the simulation. Actually, this is quite technical, so it doesn't make sense to go in detail through this. The cutoff is defined for both the Lennard-Jones and charge-charge interaction. This is how the radial distribution function will be determined. The type of thermostat, the temperature, and the time constant or coupling constant of the thermostat, and similar for the pressure. We need the bulk modulus at least approximately for this barostat to run, but it will be used in further steps. Okay, so let's run it. We'll run 150 cycles, each cycle 0.1 picoseconds, and it contains several steps. The time step was 4 femtoseconds. I missed to show you this or emphasize this. So it finished, and now we see here some graphs. So the simulation was at constant pressure already. I've forgotten this, but it's seen from the density changing, so that the density decreases. So it looks like it's close to the averaged or equilibrative value, but not fully yet. As regards the potential energy is quite similar, and the temperature increases towards the correct temperature, which is somewhere about here. So I would continue this mixing or this equilibrating so that we have a better. It looks like it's now better. It's beginning or fluctuations begin for the density. The potential energy looks similar, and the total temperature is quite good. So I will stop this and go to the next step. In the step 4, I will calculate this cluster. It will be a bit longer so that we get some statistics. We'll get a trajectory, and it's done. During the simulation, not only a trajectory was generated, but also the equilibrated size of the box, of the simulation box, is 3 times the original box, and it looks like the density at this temperature is a bit lower because this is longer than the calculated 5.7. So let's view what we've done. First, the trajectory. So once again, more slowly, back. This is the original crystal, and now it is still crystal, but we can see a lot of motion. It may be useful to make the atoms smaller to see better the structure. So this is the trajectory. I will also show the convergence profiles. They look pretty well. Of course, it would be better to run all this for a longer time, but we don't have time. Or if this is done during a normal lesson, so there is no time to do it very precisely. Few seconds is enough. The time of the simulation was 60 picoseconds. I will show you also the radial distribution function. Increase it a bit and show you the labeling of these. So what you can see here, the yellow curve corresponds to the radial distribution function chlorine and sodium. Of course, the first peak is the shortest. It's for a crystal, and these are the nearest neighbors. This nearest distance is a bit less than 3 angstroms. It is where the atoms like each other, and because there is a huge attraction between a cation and an ion, we have a peak here. The second peak corresponds in the structure of the crystal to the second neighbors, and they are approximately the same, but not fully. You can see that sodium is a bit smaller, so that this peak is a bit wider. It may be useful to show also the cumulative distribution function. We can see it here, and here is the notation. We can see here the running coordination number, sodium chlorine. If you look, I will enlarge this. If you look at this curve, you can see that the inflection point is around 6. It's not exact because there is thermal motion and some error there, and also the radial distribution function doesn't have a well-defined minimum. Still, there is some overlap at this temperature. If we use the lower temperature, we will get a better number 6 here. But 6 sounds good. There are 6 neighbors, 6 neighboring chlorines around each sodium, and vice versa. The second curve, which are of cation, and anion. Anion have the number of neighbors, the average number of neighbors, or the coordination number around 12. If you look at the crystal, you can easily verify that around each sodium there are 12 nearest sodiums. And we can continue by this, let us say here, would be 48. It's not exact. Okay, but if we simulated this at a lower temperature, this would be more pronounced. I will show also the properties of molten salt. It's not necessary for the final task, but it is interesting. You can see here the defining file for the simulation. The temperature has changed. Higher temperature will cause the crystal to melt. I can also see here that I told you a wrong value of the time step. It's 3.3 femtoseconds, not 4. So sorry for that, and let's go. Again, it's using 4 processors, so it should be quite fast. And we can see here the convergence profiles, and it looks pretty unequilibrated, clear trend. So let's repeat again. Just equilibrating the system, and it looks much better. Okay, so let's go to the next step, and it is the simulation of the melt. So again, it's running using 4 threads, and we can see the result. First, the trajectory. It looks like quite chaotic. There's no crystal-like structure. Even if I decrease the system, the convergence profiles look, well, perhaps not perfect, but much better than before. But let's be satisfied with this. These are the radial distribution functions. At the first glance, they look in the same way as for the crystal. But as a second look, we can see that the second peak here is much wider. The first peak is approximately the same, but the minimum on the first peak, which is the chlorine sodium curve, that is cation anion, here the minimum is about 1/2 only, so it suggests this is a liquid, it's not crystal. And let's look at the cumulative redistribution function, and it shows for cation anion a lower value of the number of the first neighbors. It's close to 4, but a bit lower. As regards sodium and chlorine neighbors, they are even difficult to determine, because on the radial distribution function, I will repeat it, this minimum was really very close to unity already. Okay, and there is time for the zone melting, or preparing the slab. We will start from the temperature we entered at step 3, and the system determines the size of the box. It will be used now for the dimension in the x and y dimensions of the box, but the dimension z will be changed. First, it will be replicated 3 times, and second, there will be a thermostat applied. So here the system does a couple of preparing simulations, and what it did is approximately here. That is, at the beginning we had a box with 3 times the original system, and step by step we can see how the inside of the box melted. It melted because there is a special thermostat in this case added that applies only to this half of the simulation box. Also, you can see that the box elongated. I can show this in 3D. It's not well seen here, so we must have a parallel projection. And we have everything to start the final simulation in the slab. So let's start it. Well, this is not run in the cluster, so I will interrupt it and put it to the background. So it's running now in the background, If you don't believe me, you can see it here. It's using, well, not fully 400 CPU, but a bit less, but still it's much faster than to run it on one processor. Okay, and we can show what's going on during the simulation running. So I will show it from the start slowly. So essentially there are a lot of fluctuations, but still there is a melt and a crystal. This simulation will be a bit longer. I can show you several such simulations at once, and on this graph what you can see is the density as a function of time. The time is in a nanosecond in this case. White, yellow and pink results are previous results for different temperatures. This is a low temperature, and you can see that during time the density increased until this value corresponding to a solid crystal, because it has a higher density than a melt. But for this higher temperature the density is quite low, and the yellow one seems to be close to the melting point. So let's see what about this cyan or light blue. So I will now stop recording, and let's wait to this a bit later. After about 6 or 7 minutes we are getting these results. The simulation I have started was for 300 Kelvin, and it is light blue here. We can see that the density, which was originally about 1040 kilograms per cubic meter, within a bit more than 1 nanosecond drops to this value, and it corresponds to a melt. It can be compared with another simulation for a lower temperature, 1250, the yellow one, and after about the same time the system froze, so that we can conclude that the freezing temperature is 1275, with some uncertainty, of course. Thank you for your attention.